Hello everyone, I am Anita from 4th year EC department, and in this video we'll have a detailed look on what LZW coding is, the mechanism behind the working of LZW coding, and we'll also look at the Matlab demonstration of LZW coding. Before we move on to the topic, let's have a look at what data compression is. In data processing, data compression is a process of encoding the given data so that we could reduce the number of bits that are required to represent the data. If the size of the data is really small, we might not go with data compression, but in case of large sequences such as videos or images, we go with data compression so that we could reduce the hardware required for storage and also reduce the transmission time for the data. Any particular data can be lossy or lossless depending upon the compression technique we use. So in case of lossy compression, the original data we remove from the original data we remove redundant or useless files. So whenever we try to restore the original data, we couldn't get back the original information. But in case of lossless information, we do not remove any kind of data, but rather use proper compression techniques with the entire data intact so that we could get the complete information when we try to decode it. So in data compression, we have this original data. We then compress the data using suitable algorithms. We have various algorithms like Huffman coding, LZW algorithm, or run length encoding. Then once we compress the data, we transmit the data or store the data, and when required we then decompress the data and then the original data is recovered. So practically we see data compression everywhere, and one such example is in the Blu-ray disc, where we store various HD files of very large size in a small disk itself. So this is where we use the data compression. LZW coding. LZW coding is a popular compression technique which is known for its easy implementation. It mainly focuses on producing error-free compression. So how LZW coding works is, initially we will be having a sequence of images or strings, and then using that and using a dictionary, here we encode the given sequence so that while we are trying to represent the sequence, the number of bits can be reduced significantly. So one such advantage of LZW coding is that we do not require the probability of each sequence. For example, in Huffman coding, we do require the probability of the sequence when we try to encode the bits. As we have already seen, LZW coding uses a dictionary to store the sequences which are unrepeated. So from 0 to 255, the sequences are represented with the single bits. So whenever we encounter a new sequence that is not present in the table, we just store it in the dictionary. For instance, let's just say we have the sequence 255 and 255 which is not present in the table, and then we encode it and store it from 256. So in that way, all the sequences which are unrepeated are stored in the table from 256, and a suitable encoded output is given to the code. Let's now look at an example of LZW coding. Here we have a 4x4 8-bit image of the given sequence. So initially we have pixel number 39, and since it's a single pixel without any sequence and it's already present in the dictionary, we do not encode it into the dictionary. And then the next bit we have 39, and its previous pixel is of 39, and since the sequence 3939 is not present in the dictionary, we place it in the dictionary at location 256, and its encoded output is 39. So moving on to the next bit, it's 126. The previous bit is 39, and since 39 126 is also not present in the dictionary, we now place it in the dictionary at 257. Next we have bit 126. Its previous bit is 126, and since this sequence is also not present in the dictionary, we just encode it and place it at 258. So this process continues, and whenever we encounter a new sequence which is not present in the dictionary, we continue to place it in the dictionary at suitable location. For example, let's just say we encountered a sequence which is already present in the dictionary. See, here we have 39 and 39 which is already present, we just don't encode it, and whenever we encounter this sequence, we just replace it with this encoded output while we are encoding. Let's now look at the Matlab code for LZW coding. So initially I took an image as an example which I have seen in the previous slide. I converted it into a vector so that I could easily perform the operations on it, and then passed it to an encoder image. Let's now see the main function here. So initially I started indexing the vector and selected the element of the vector, and I tried to identify if that particular sequence is present in the table or not using this getCode function. So this getCode function returns yes if the sequence is present in the table. So if the sequence is not present in the table, we add it to the output table or the dictionary using this add code function, and after that we print that particular sequence. If the sequence is already present in the table, then we just print out the sequence without adding to the dictionary, and then we continue the loop till we reach the last sequence. So the code for this get code function is here. So initially if the length of the substring is 1, that means that if it's already encoded in the table, then we just copy it into the code and then pass back. If the length of the string is greater than 2, then that sequence means that it's new and it's not present in the dictionary. So we just bifurcate the given string and divide it continuously and find if that particular string is present in the table. Let's just run this code. See here we can see the various elements which are stored in the dictionary, and right from 0 to 255 we can see all zeros, which means that no sequence is stored from 0 to 255, but right after 255 we could see the elements stored in the dictionary. So we have the sequence 39, 39, 39, 126, this 3-bit sequence and this 4-bit sequence which I have seen in the previous table. And we also have this coded sequence with the index and also the sequences which I have seen in the previous example. LZW coding can be applied on strings as well. In this code, we have taken a string example and then we reshaped the string so that we could perform the operations on it, and then passed it to the function right here. Moving on, the working of LZW coding for string is similar to that of the vector, where we consider the initial element in the string and find if it's present in the table or not. If that is not present in the table, then we add it to the output table here using this getCode function, and if it is present in the table, we'll just print it out. Let's just run the code and see how it works. As we can see here, we have the elements right here and the respective symbols, and we have the encoder output right here, and the new symbols after encoding were also listed below. Moving on to the advantage and disadvantages of LZW coding. The main use of LZW algorithm is that it does not require any previous information or the probability of the sequence like we need in Huffman coding. Further, it requires less time for execution and it provides more compression ratio compared to the Huffman algorithm. Since LZW algorithm is a lossless compression technique, we do not lose any kind of data, and the encoded sequence can be restored easily using decompression techniques. But however, one of the disadvantages of using LZW coding is that it is useful only for large amount of text data if the redundancy is high. If the repetition is very low, LZW coding does not make any significant difference in the encoding. And also other disadvantages is the size of the dictionary. If the size of the dictionary exceeds, we have to replace the dictionary by another new dictionary. Moving on to the applications of LZW coding. LZW coding, we use it in GIF or PDF formats, and we could also modify LZW algorithm with Huffman coding to provide more compression rate. That's the end of video on LZW coding, and thank you.